my goal here is that your grade should reflect, typically your grade should reflect what you would have gotten had that particular question been on an exam, right? That would be the idea of saying how well did you adhere to what the procedural process was in place. Part of the reason why a degree of robustness for both representation and the process involved with it, reason why I wrote the assignment up in such a way as to request the task records is I think the only way that you can really understand the process is to approach it in a scientific way, right? As humans, we can really only understand relatively single factor processes. So attempting to change both the network topology and the learning rate simultaneously, not really gonna make much sense to you, okay? Changing the learning rate by big chunks at a time, also not gonna make much difference to you. It's gonna seem like it has quasi-random behaviors. So what you really need to do, or really need to grasp out of this, the core thing that I want you to take away from, if you got some negative feedback on this one, or it didn't align with what you expected, we'll make adjustments for it because we're still early on in the process. It was our first of our submissions. And we're going to have more submissions, all right? We're going to have quite a few more. But my goal is not to create a punitive system in which you feel like you've got to get it exactly right in order to feel like you learned something to move on. That's not the point. I do make considerations, and I do give feedback, and sometimes I come back and adjust things long after they've already been due and done, right, in order to be able to make up for points and spaces where they might have been lost. We're in process, and I'm in process of adjusting any of the scores that might have lost points based upon anything that's baselined there. But the key factor is we're going to make sure in the future, two things. One, I will personally make sure to have more clearly defined characteristics of saying exactly what is expected on your end, okay? Because that's a situation where I want to make sure it's easy for you to understand what I hoped you to do in the process. I think this last assignment was more of a tutorial / fact-finding mission for you. Some of you took it on in that way and took it on as something to sort of just experiment and play with. But at the same time, it's an experimental space as well, right? We have to approach things from a scientific standpoint. So that procedural process, that notion of saying, okay, I'm going to start off with this network topology, right? You guys are doing network topology now, right? You're changing the number of nodes in the layers, and you're also doing what? You're changing the learning rates, okay? Changing batch sizing. You have basically the same set of parameters that you're working with in the TensorFlow playground. If you guys are currently engaging in that assignment in the same way that some of you had went after approaching the numbers in the TensorFlow playground, I'm sorry, okay? Because you're wasting immense amounts of time and you're avoiding learning. The reason why I say you're avoiding learning is if you were to take on, think about this in your own head, what other process that you wanted to try to comprehend would you take on by just changing random stuff? Nothing, you wouldn't. Treat this as a procedural process where you attempt to understand, if I change this thing by this much, what happens, okay? Stop changing 5 things at a time. Don't change the number of nodes in the network. Don't change the number of layers. Don't change the number of features you're pulling in. Don't change the learning rate or the batch size all at the same time and expect that all of a sudden it's all going to work out, okay? You don't backpropagate. Your brain does not backpropagate all those 50 features simultaneously and figure out the right permutations of those numbers. If you want to think about it, possibly the best methodology that you can employ for that particular case is to do an iterative methodology, right? Test 1 node, see how it converges. 2 nodes, see how it converges. 3 nodes, see how it converges, okay? Then start back over again. Learning rate slightly smaller, 2 nodes, 3 nodes, 4 nodes. Learning rate smaller, 2 nodes, 3 nodes, right? If you want to, and obviously you guys are all by far sophisticated enough to implement this, all of those variables are assignable. All of the outputs from those systems return both an array that can be stored, right, and a network that can be stored. put it in a for loop. Put that for loop in a for loop, put that for loop in a for loop, okay? And then you can run the entire experiment iteratively, such that you can see what happens as each of those parameters change. Somebody asked me a little bit ago, when are we gonna learn about hyperparameter optimization? You already are. Those are what are considered hyperparameters, okay? How many elements are in the layer? How many batches do you want to train, right? How big are the batches? How does a batch affect something else, all right? Krishna and I were actually looking at the book and trying to figure out what the book taught you guys about batch processing. And the answer is almost nothing, okay? How many people have been reading the book? I'm not disappointed. I'm not even remotely disappointed.
A little bit.
You did?
A little bit.
Yeah, a little bit.
A little bit. A little
Same.
bit.
I started reading on something. So I read this book when I was taking this class back in like 2015, right? It was still in like preprint at the time. And there were some errors in it and stuff. And I remember actually one of the guys that was in my class with me made some suggestions to update the book. And they, they're still there, the same changes. But I started reading this book and I'm like, the level that they expect you, level of understanding that they expect you to have of all different kinds of methodologies of machine learning is crazy, all right? They started talking about, so the passage on batch specifically started talking about how dropout normalization methodology was a similar process to bagging. And it's like, okay, well you have to look at it with respect to how bagging and boosting operations work. And it's like, yeah, okay, that makes sense if you're talking about forest and optimization.
Yeah.
But if you're thinking about it from the standpoint of saying, I want to try to teach you for the first time what dropout and batch normalization are, right? I can't start off by comparing it to this other complicated thing that you have to research. And it becomes this process, a bucket brigade in and of itself, right? It's like, it's back propagation until you get back to whatever level that you actually understand at, okay? What I like to make this akin to, or I like to try to explain it being similar, is the notion of installing a package on your Python, right? Or any other embedded system, right? What happens when you type in, pip install? What does it do? It goes and it looks at your environment and it says, what do you already have installed, okay? What are the versions of them? We call it dependency analysis. You guys all have to do this constantly and you don't even think about it, all right? Because learning is a constant dependency analysis framework. Every time a new topic comes in, every time you get something new that you have to try to install in your brain, you're going to look and say, what do I already know, all right? And how does that integrate with what I already know, right? Do I have to totally figure this all out from naive, total scratch? I have to understand it from most basic terms in general. Or can I take some of the information I already have and draw on that knowledge to create a more complex structure, more robust and robust understanding? This idea of having constant chain requirements, constant sets of chain dependencies in these spaces becomes problematic and frustrating for some of you. I recognize that. You go and you try to look up the definition of a terminology and you say, hold on. The first 5 words in this sentence, all of them require me to click on hyperlinks to go back to be able to understand what that thing is. Okay? I know it's a little much, but keep in consideration that many of the things we're doing now have only technically existed for about the last 6 years or 7 years, right? Right? Maybe we go back to like 2014, so about 10 years. For some of the vision processing systems like convolutional neural networks. With respect to the way a lot of other sciences work and with respect to how cutting edge this topic actually is, that's one of the situations where I go, give yourself a little bit of break, all right? You're not expected to understand it immediately. Sometimes you're not even expected to understand it other than probably have a grasp on it toward the end of the semester. There is a moment that will happen for most of you, I hope happens for most of you, that while you're working through a project, you will see some results and you'll go, I get it, right? You have your, I know Kung Fu moment and just like, be able to see what's happening, like, wow, like it makes sense, all right? those little bursts, those little epochs of being able to make it all clear at the end of the process will happen for some of you along the way. That's my hope for everyone in general, all right? For the moment, focus on figuring out scientific methodologies, procedural methodologies for doing your work with the networks. Let's stop with the shotgun, scattershot, random, play with, adjust values, considerations we ended up with on that second assignment, okay? That is really when I look at it and I say, how seriously did you take it? Well, I knew the point was to get you to play with it. I knew the point was to get you to see it doing a thing, all right? But there's actually very little difference between this second assignment and that first assignment. But one of the reasons why I gave a little bit of additional space on it is because of the fact that I wanted to have this conversation with you, in that if you are throwing spaghetti at the wall and seeing what sticks, all right, just doing random crap and hoping something happens, you are not actually learning what the internal processes are. There are aspects of it where I say you can get an intuitive grasp, right? I have a feel for how many nodes a network requires in order to be able to solve different kinds of tasks. I have a feel for what the learning rates are for convergences. Roughly, most of the time, they work out. Occasionally, it's stochastic, right? So it's still random. So here's the thing, here's another consideration that I want you guys to put forward here. Let's imagine something and say, imagine that I just did one run of one configuration, one learning rate, one batch size. Do I truly understand how that configuration works?
No.
No.
No, because the initialization was random, right? And that random initialization is going to have a different set of internal convergences to local minimum. That's the consideration that I want you guys to put forward, maybe even more so than anything else, is you're going to have to observe these networks as they operate and see whether or not there are consistent characteristics in the multiple different runs of the same configuration that tell you something about what's going on in the mind of this little creation, okay? Many of us want to just get it over with as fast as possible. That's not necessarily the point of these exercises and activities. What is the point of your college? What's the reason why you're here in this class? The reason why you're taking this approach to this process? I know many of you are going to answer, I want to get a good paying job, okay? And I appeal to you guys as much as anyone else, because of the fact that I tell you that being able to explain this stuff well, having a real grasp on it, will translate to those interviews, and it will translate to those jobs you get, and those jobs you get will require you to have that skill, right? You have to have an intuitive grasp. You can't just go in and start doing random numbers, right? And you show this to your boss and say, yeah, maybe like, why did you change the topology of the network 2,700 times, right? like this seems like it changed every single time you did it. There's no rhyme or reason to it, And so you're like, well, I was just getting a feel for the network. No, that's not gonna fly, okay? Yes, we know it's more art than science, but there is a skill, all right? And this is a term that Dr. Durakshani, who is my advisor, who's a guy that taught this for a long time. It's a term that I really like, it's a term I use a lot, and it's called jobfuscation, okay? You know the term obfuscate, right, to hide something,
Yeah,
right?
jobfuscation.
So jobfuscation is when you obfuscate your actual job, right? So technically what we're doing is a bunch of randomness in the background, right? But it's controlled chaos. We control the chaos, right? But you don't tell your boss that, okay? So in truth, you have to figure out how to translate from this somewhat chaotic entity that you're attempting to exercise control over, and the quality of the output that it has, and the fact that you're doing something procedural, intentional, to develop something that goes in a specific direction, right? It's like handling an animal. The argument that I put in place here is that if you're afraid of these networks a little bit, and I say afraid of them in the sense that when you're afraid of something, why are you afraid of it?
Because it won't work.
True, but let's go from a different perspective. Let's just talk about animals. Let's talk about snakes, all right? Why are most people afraid of snakes?
Because it will bite.
They bite.
Exactly,
And they
all
can
right?
be poisonous.
But there are people out there that are not afraid of snakes. What's the difference between us and them that are not afraid of snakes? The professional snake handler that picks up the snake and goes,
They got
"Quality
skills."
is beautiful," they're not
They
just
got the
crazy
skills.
people. They're not just crazy people. Why is it that they can handle the snake so easily?
Because they got the skills to handle them.
How do they get the skill? They did it frequently enough that they understand the behavior of that animal.
Yes.
Okay? To us, because we encounter them rarely, their behavior seems random, it seems aggressive and all these other things, right? But when you understand the function of that animal and the way it's supposed to work and the environment that it's built in, right? You characterize it, then it's much easier to handle it, all right? These kind of networks have so much flexibility, they're much like snakes, right? They will bite you. They will, and they can be scary. But when you get comfortable with them, when you learn what they do, you learn how sneaky they can be sometimes, and you learn to wrangle them. You get your chair out and your whip, and you get them back in their cage, all right? Then they become a tool for us, right? Many of you guys have probably know about, or at least have seen kind of communities where oxen are used as farm animals, right? Oxen are super powerful, right? And they're also very stubborn. So you have to do what? You have to latch them up to the equipment and you have to drive them in the right direction. So this is powerful stuff that's very stubborn, and you have to figure out how it works and get used to dealing with it. And you're going to do so by approaching it in a logical fashion by which you test around the sample space, get a full comprehension of what is available to you, what tools you actually have to play with. What things can we adjust inside the neural network? Are we going to go in and change the weight of a specific connection? No.
No, we can't.
You can.
Well, you can, but it's not.
What would be the point?
Yeah,
Okay?
exactly.
So I say you can do it, and you can watch what happens. That's an interesting experiment. Try it. Right? Go to your TensorFlow playground, actually go in, stop it, change your weight around, set it to 0, and watch what happens to the network. That's one thing you can do. With the system we're dealing with right now, we have number of epochs. Right? Something that was mentioned to me earlier on. Does number of epochs mean better model? Yeah, right? The longer you train it, the better it is. No, not true, okay? Don't just set epochs to 1,000 just because of the fact that you imagine that's going to be the case. Now, one of the things that's interesting here is this is a very unsophisticated methodology of implementation of the network, right? It's very low level, I guess you could say, in the effect of saying we're really kind of handling all of the instantiation and everything directly hands-on. We're building the layers and all this stuff with individual functionality. The reason why that's a good thing is because it just gives you a grasp, or at least you can see the functions, how they're generating the outputs. But it's missing a couple of things that that would be considered as kind of like quality of life improvements for the model training paradigm. Stuff like momentum, right? Keeping track of the weight updates. Did you guys see momentum before when looking stuff up? How many of you guys are using external resources besides this class? Okay? If you're not, I really want to see that hand up. Because I guarantee you this, I'm doing my best, but I cannot teach you everything. 100% total God's honest truth, there is too much to handle in this class in one semester. I am steaming through it at an incredible rate because I want to get up to the points where we can have conversations about some of the cool upcoming methodologies. What's one of the problems with that? I showed you some of the topologies of some of those networks. The things you start talking about at that point in time become borderline philosophical. Not even technological, right? What makes up the universe? How complicated are functions and structures? What's the minimum requirement in order to adequately model something that has this level of systematic complexity, or this level of variance, this level of entropy? We have to be able to make considerations on what actually exists in the physical universe in order to think about what we're going to get as an advantage or disadvantage out of this space. What happens when we start dealing with systems that aren't just static environments? What happens when they start to change? Then we have to deal with recurrence. We have to deal with keeping track of states and updating those environments based upon past inputs. That gets incredibly more complex than even what we're doing right now, okay? So what I'm asking you kindly out of all of this stuff is use some resources besides just the things I'm telling you, right? If you need another couple of textbooks that might work, I will try to find you something that I think is maybe a little bit better than the one you're on right now. Not to say it's a bad one. One, it's free. Two, it's written by like one of the greatest minds in the era, right? But the problem is, this is also one of the people that developed this stuff. So they're talking about it as if it's like, come on, it's obvious, second nature, right? You want to know all these other things that led you up to this point in time. The reason why is because the audience that they're writing these books to are who? People that have probably been in this space for a long time and have been using a lot of those other tools beforehand. And now when they're coming to these tools, like deep learning, they're going, wow, look at all the things it can do that I wasn't able to do with previous methodologies. They respect and understand both the necessity of having a complex model in order to be able to take into consideration the flexibility necessary to encapsulate the variance in the world, right? But they're also very respectful of that problem that would occur, that would happen whenever you just put 1,000 epochs in on the model, overfitting, right? They don't concern themselves entirely with getting a maximization on performance in the model. They have much more comprehensive sets of metrics they're taking into consideration, right? Quality, sensitivity, specificity, all those things that we utilize for classification and output training methodologies. So use your skills to get online, find some resources. I'm trying to make it as simple as I possibly can, but I think one of the things that I would say is probably obvious is when you actually got ready to sit down and start doing it yourself by hand, you go, wow, this looks it's a lot harder than it looked on the slides, right? But the slides are there, they're key for you to work off of, okay? And it's kind of the example I gave you is kind of in between two sets of the slides because it's got multiple values in each of the weight systems. But if you can do each of those partials for the backdrops, you really can handle doing it from there, all right? We will then move on to how you deal with incredibly high dimensionality multivariate outputs, and those require the tricks that I'm building out in the videos that I've been working on for you. I know I've been stretching those out, but I'm stretching those out for the consideration of making sure you have the fundamentals before I institute those things that we're doing that are effectively tips and tricks in a way. So we don't want to go and calculate every single partial value for every single value in the system. So we're going to have to use some tricks and some shortcuts to be able to save ourselves some time and get the most likely estimate of the gradient for the system rather than getting the exact gradient. You guys are calculating the exact gradient, exactly how much the partials compose to in order to be able to get exact value for the weight update. But here's the thing, I don't have to do it all at once. I don't have to make all adjustments to the error in every single optimization space. So as a result, I can do some now, right? And if I don't get it all now, I'll pick it up later. So a close enough approximation, right? 90% today is a lot better than 100% later on, right? 70% solution today even is much better because we have time to attempt to update it and adjust it in the intervening period. So from a computational standpoint, the things that we have left to show, or the things I have left to show you for the derivations are going to be deriving the rest of the backprop proof, deriving the Newtonian method, right, for the SGD, and talking about how the Laplacian of the matrix decomposition for the partials is a trick or tool that we can save some time on, right? And then we'll integrate that for complexity with respect to that, the full solution for the universal approximation, and tie that into how we're doing the kernel updates. Okay? I'm going to try to tie that all back together. How local gradient optimization is utilized in that space in order to fix and adjust for some of the things we're dealing with in the other spaces. Okay. I want to just go ahead and talk for a little bit today. I know I haven't really even started projector yet, but I'm going to talk for about half an hour. But I hope you guys get across a little bit more of what I'm meaning, or what my hopes are for how you'll approach the research of this particular topic. Because it's like any other set of information. There's a ton of tools out there for it, and you're going to have to try to find your own diverse ways to be able to look at it. I know that there's a desire where you say, oh, I should try to be able to find all the solutions to all the things that are necessary along the way in the classroom, and say, no, I can't really do that. I can't guarantee that I can give you absolutely everything you need. All right, let me tell you this. This one's probably dark enough. I might have to turn off the rest of the lights, but I think that might be okay. Some of you may have already seen this. but I want to go ahead and walk through it anyway because I want to talk a little bit more about what the outputs of the convolutional layers look like and how it relates. We are going to actually implement in our next assignment a version of the MNIST problem in both a vectorized form as well as a convex form, okay? So we're probably gonna do that in like maybe 2 steps or 2 parts. So I might sort of assign it, you know, kind of together and then it comes in 2 separate segments where start off with the vectorized version and then move on to the convolutional version along the way. I want to start building this into more monolithic sort of projects because we're ultimately going to get to the end of the semester and I'm going to give you guys some data sets to choose from and then I'm going to give you the opportunity to compose what you want to do with that project, right? Pitch it and then generate those projects for the outputs, right? What does the topology need to look like? Can you transfer learn it from another learning environment, right? Do you have the resources and hardware to train it or do you need to put it in the cluster, right? Depends on the complexity of the model you're working with. We will actually be able to, there is afforded to us the ability to work in a cluster, to be able to do compute operations. But one of the things that I've noted thus far is that most of the relatively rudimentary, even CNN operations can be accomplished in Colab, all right? And they've already got a reasonably well-performing version of TensorFlow already working in that space. So it's not really super necessary for you to do a lot of this stuff on your local computer, but it is relatively useful, all right? So our input space, all right? Input space is sourced from this sort of drawing space up here, right? And if this system is trained to output, right? What is it trained for output for? Well, it's trained to output numbers, all right? 1 through 9. Let's look at what we have from the end of the system, right, to back to the front. Notice something about this. There's already strength of connectivity to connections to this feature space. Why am I not drawing in something yet? Well, the reason why I'm not drawing in something yet is because I want you to look at what we're actually seeing for the connectivity of the outputs.
Can I shut down the light? Because
Oh, you can probably see it well enough there, can you?
yeah.
Okay. I just needed to zoom in a little bit more for you to be able to see it a little easier. Notice the strength of the connections between the components of this vectorized input. That's a fully connected network, right? It's a fully connected layer. It has 10 outputs, right? And then it has, I'm not sure what the dimensionality of that is. I know it's a lot more than 10, right? I think it's like maybe 50 to 100 or something like that, okay? We said this is a convolutional neural network, right? What's this doing in there? This is a layer, a standard layer within a neural network, right? It's just a flat vector to another vector. This is how we classify, all right? This is how we have to classify because there isn't really a methodology to drop the feature characterizations out in a way that allows you to do a kernel operation on it, right? We're technically doing a linear operation to linear input. As I said previously, by the time the data gets to this point of the network, it's already contributed to by a bunch of different things. So right now I'm on 8, and I note that this particular node right here seems to be the one that has the highest connectivity to 8. Okay, so let's go down and see what happens. Notice that feature gets its information where? From multiple different locations, right? Each one of these having a slightly higher weight connection, right? Intensity being the indication of the components in place. So if those neurons are activated, right, then that neuron activates, and then the summations relative to the linearities that are connecting the other feature components to the next layer will feed out to do what? Activate that layer 8 element at the very end with a higher degree of activation relative to the likelihood of that particular drawn feature image to be considered the number 8. What is the operation that's happening at the very last component there? What would we call that? What would be the likely integration for that linearity to those 10 class outputs? What would be the activation function? Softmax. Yes. Why? Anybody disagree? Could we utilize anything else? Yeah, we probably could. We could probably get away with using a binary output, okay? This is a weird one. I could have one classifier for every single letter, and I could have a binary output that says either it is that one or it isn't that one, okay? So that would require me to have 10 different models, each one comparing them together and taking whichever one had the highest likelihood of being in that model space. Seem a little overkill, just using logistic regression? Guess what, it's exactly the same thing. Each one of these is a logistic regression based upon the log likelihood of that set of features to compose together to become that particular number. Softmax is in fact that. It is in fact a coalition model. The only difference is I don't have to have a different set of layers feeding into it. It's vastly overkill, right? And for any of you who remember what those models were called, remember those? Bayesians, naive Bayesians, right? Naive Bayes built a binary model for in versus out for every single one. Every single one was a one versus the rest classifier, okay? There are tools that require us to do that, and it's interesting whenever we get into very, very large spaces, sometimes it's actually relatively beneficial to have one recognition node that is specifically targeted towards isolating that particular output. We'll look at that whenever we get into talking about the idea that we're going to do localization within the original image frame, okay? So I'm going to go ahead and draw an 8, and we're going to see what happens to these nodes. Uh-oh.
Oh no.
I'm apparently terrible at drawing.
Oh no.
Let's try it again.
You classified it for me.
There we go. All right, what's the first rank? First rank's an 8, right? Second rank is a 2. I can see maybe the reason why. What do you guys think?
Yeah. I mean.
There's a couple here. These two seem like they have relatively high connectivity to 2. What might those be? If we're decomposing this back to thinking about what portions of the drawn image each of these activations refer to, we notice that the 2 and the 8 both have a curvature on the top,
Yeah.
right? So I say maybe that makes sense, that there would be, if you think about it actually. So you have, this is the 2, right?
Yeah.
The 8 actually kind of starts the same way,
Right, and then it.
but I
moves
come back
back
around
up.
with it.
Yeah.
So the 2 has the same component here of the 8, right? Such that it's made up of all the components that, except for that little crossover piece there. So technically, yes, it makes sense. If we break this apart in our heads, we can say that the items being recognized within this sequence fall underneath those lines of thought. So what should happen when we get down here to looking at the components that make up the elements that feed in to those features within the layer? Let's look and see. So we know this one's pretty active with regard to 8, right? This one also does a pretty good job to return to 8, right? So let's see what else is involved there. Let's say those 3 right down here in the bottom, okay? See how those integrate to this. They are connected to chunks of spatial information, okay? That honestly don't make much of a difference for us to look at when it comes to connectivity.
Whoa.
Okay? Yeah. So that's a lot of spatial information being reduced down to a very little amount of information that's being represented on that graphic space. What's one of the problems here? How do we make sense of that many pieces of information being decomposed into a singular feature at that point? Notice, let's go over here and look. Let's start looking and seeing what we're actually looking at toward the end. And that stuff look like an 8 yet? I think it looks like an alien wrote something to us.
portions of the 8. Maybe.
Is that it?
Yeah. That little curvature thing.
Yeah.
Yeah.
So why, it found the 2.
Found it too.
Found the 2. It activated on the region that was similar between the 8 and the 2 with respect to the feature components that made it up. So the primitive components that were making up the larger composited image, the edge feature components, were brought out early on in the process. Like I said, these ones here are interesting because if you look at them, and then you look at the matrix that's below them, you can kind of get an idea of where they came from, right? They don't have the same types of connectivities, okay? They are only linked to the layer below them. So what kind of layer is this?
So, I guess I'm a little confused because I thought a CNN gets smaller.
I'm going the backwards direction. I started from the output.
Got it, okay.
We're back propagating the CNN. For those of you who had already seen this before, right, this is maybe a little bit of a novel approach to looking at it the opposite direction rather than going from the big version to the small version. I thought maybe let's go back the opposite way, okay? What is this? What did I just do? So I took a matrix and it got smaller. What is it? Maybe that one will show you a little better.
Yeah, it looks like it's a
Filter.
Is it a filter? You tried. I appreciate the intent. Appreciate the intent.
Max pooling, right? It's taking like.
It's max pooling.
Yeah.
Right, correct.
it's taking.
It's a 2x2 max pool operation. Okay, so it's a downsampling rescaling operation. Downsampling with max output for the local area. So each of one of those points is representative of 4 individual points in the original space, taking the max value as represented in the area. Notice the feature components there, they're all zeros, right?
Yep.
So it should be 0 on the output, right? That's relatively straightforward.
Yeah.
The other ones, though,
It could be.
we see at areas where we have some degree of fuzziness, right? This little area of fuzziness here. We've got a couple of little purple one down there on the bottom, so we get something that's kind of
In between.
vaguely purplish, right? But notice we have radically reduced the spatial representation here. But look at the difference between the density characteristics of this. This has a lot of sparsity, right? There's a lot of spaces that aren't filled with anything. Okay? Normal real world has what? Lots of space, right? Technically, the natural universe is more space than stuff. So in a sense, here's the other portion of it that's interesting. Sometimes the space is as descriptive as the stuff. Barcodes are an example of this, right? The lines don't matter. It's the spaces in between the lines. The spaces in between the lines actually define the code. The black spaces on the barcode are blockouts. So they're the spaces, they're the black elements. So technically a barcode could be represented in a denser matrix format. You've seen one of these before. What are they called? QRs, right? QR codes.
QR code.
Technically, these are a type of QR code, right? This sequence of structured information represents or is correlated to some specific set of feature information, right? In the case of a QR code, it's a very specific set of high and low intensity elements, right, that structurally tell us what's supposed to be there. This is sparse, lots of extra space, right? This is denser, but retains what? It retains the characteristics of the original information at a lower spatial representation. What do we like about this? Less compute power necessary in order to process anything that's at lower dimensionality. When you reproject something down to lower dimensionality, you say, hey, I can process it in a fraction of the time as I did beforehand. So this idea of spatial reduction is not just the process of reducing the components of the space, but it's a process of reducing those components such that the maximum informational quantity is retained through this process. Notice here, this one's really impactful to me.
Yeah.
Look how sparse that matrix is on this side right here.
It's,
Notice how much information is up above. We've taken all that crap, spread over all this whole area, and then what?
Just-
Stuffed it up into something
Yeah.
useful.
group them together, kind of.
Now, what's one of the problems with this? We did remove the spatial information. Why is it that we said we had to start off doing this with regard to convolutional neural networks? Because we had to retain the spatial information, right? Because just vectorizing it wouldn't solve that problem. Now we've crammed it up into a lower space, seemingly regardless of its spatial configuration in this 2x2 area, right? Such that 2 pixels beside each other were previously in 8x8 space, or an 8x8 area, right, can now be directly adjacent to one another in the output space. Totally dissolves all of the other area around it and compresses large chunks into smaller chunks, right? Without regard to where they were originally located or how they were co-located. How do we resolve for that? By doing it a bunch of times, okay? That's the only thing that really makes any sense to me when it comes to the explanation of what's happening here. There is loss. When we compress, when we drop down the elements involved in the system, we are going to lose information as a result. But that information loss is acceptable because of what we've done, all right? The initial process, I'm going to zoom out here again and look at it, so we can see what the comment looks like as well, right? So here's the whole version. We've been looking at the nitty-gritty details up above. This network, or this process shows the network all the way through its process. The initial drawing, the digitization, activation, operation, to all these different versions of the 8 being shown here. What are those different versions of the 8s? Filters! Good job. Good job. Your moment to shine. Okay. They filtered it.
Yeah.
What does it mean? What do the filters mean? Okay, imagine that the 8 was like made out of a pool noodle, okay? And you have a flashlight, and you're sort of dragging the flashlight around the pool noodle and you're watching where the shadows get cast. Different shadows that get cast as different surfaces allow us to understand how the intensity of the surface changes as we're moving across it in different directions. So the filters moving across it are a bit like the passage of light over top of the surface. It gives us both structural information and texture information based upon the frequency of the components as we extract the edges out of that original image. So while initially it's a little vague what we're looking at in the fuzzy little grayscale version that I drew up in the top, this digitized version down here has hard lines, but it has hard lines in a lot of different directions. Whereas the inside versus the outside for setting up the binary matrix that tells you where one line starts and stops in each of the relevant directions. So by integrating different views together, each one of these different views has a different set of informational characteristics involved in it. And the very next operation that we're going to do is what? Crunch it back down again. So each one of these is a kernel operation striding across the surface of the image, indicating, right, like the indication here is what? As it's leaving the surface, as it's leaving the high edge of the 8, it indicates a high transition, a high to low transition. So the activation of this kernel in that space right there, I'm going to zoom in on it again, we'll look at from the bottom up now. As the kernel is getting ready to leave, right, notice I've got activations in the center, those are all dark activations, right? But as I get ready to leave, as I'm moving across, because the kernels do this, they walk across this way, right? So when the kernel's walking across this direction, it says currently all the elements are high intensity, so nothing's changing. So the convolution doesn't result in any change in value until it gets to an area where, what? It's walking off the high surface onto the low surface. That's the shadows cast by holding the flashlight kind of right above the system, right? It should kind of maybe up and off to the side like this, right? Shadow down here in the bottom, the offset transition, shadow in the center, shadow for this transition, that transition, and then the ones on the bottom side over here. right? The light is shining off and casting shadows on the surface behind it. We're using the shadows and a composition of a bunch of different viewpoints, effectively, that we've created synthetically by adjusting the lighting angle, if you will, around the outside of it, by multiplying it by that convolution kernel, right, that filter operation. By doing this multiple different times, we end up with multiple different views, right? And then we even further expand by convolving again by even more kernels. Right, so each of these are subsampled down, rendered down. Once again, we saw the nice operation here where all of the useful information is kept, sparsity of the matrix is significantly reduced, and yet we still have nice, big, fat activations on the top here, showing us where all of our transitions are. Think about what this one looks like. Both an edge leading in and an edge leading out as it goes across the top here, right? So it sees the edge leading in and the edge leading out. This is probably something like putting the flashlight kind of directly above it and watching as the light falls off of either side of it. Technically, I'm oversimplifying it in a sense, because not all these totally work out where it's like perfectly like what would happen with a 3D object, but you can kind of track what the point is, right? It's when do you start to enter the space of the object, when you're leaving the space of the object, how does that work as you're moving over it in a specific and metered fashion? If the network is moving through it and extracting its information about how this thing is put together, step by step, iteratively improving its understanding, what should be our job? Exactly the same thing, okay? Step by step, iteratively understanding how this thing is working. So when you make small changes to the system, look, see how they're characterized. Watch it train for a couple epochs, then maybe go in and look and see what happened to the weights in the system. If you have those tools at your ability, which most of you guys probably can pretty easily find the quick solutions for dumping out this stuff and even do the network visualization, which, well, I'll add you some scripts for those. Stuff like showing you what the network looks like and maybe even showing you like up to the minute timing methodologies. TensorFlow has a built-in graph visualization, which will show you the accuracy of the model as it's training through. And it can even output the visualizations of what the network topology looks like. Not quite like this, all right? This is pretty unique to this case. One guy built this and put this up on GitHub originally, but now it's only available on his website, so I'll give you guys the link for this. But you can draw your own, see how all this stuff works together, and see how these original systems end up getting reprojected using kernel operations, okay? So the interesting part about these is that the kernels start getting very specific. Originally, most of the information here was designed to try to extract just large global feature characteristics from the original system. These systems of the next kernel space start getting very, very fussy about where they're pulling their information from, right? And where the highest activations are in each of those cases. So those features are made up of components, and notice the size of these kernels. Pretty big, all right?
Still pretty big.
Pretty big kernel for a relatively small image, right? That's countable pixels. And that kernel goes what? I believe that's a 10 by 10. No, maybe. I think maybe those are 10 by 10s, or maybe 8 by 8s. All right, so we got 8 by 8 kernels. All right, that's a big chunk of kernel. Reason why? Because the features that you're looking for are incredibly large with respect to the visual space. So whenever you have large features with respect to visual space, you need a bigger kernel to take those into consideration. Because otherwise, they're going to be too big to get picked up by a smaller kernel, right? So as we recombine, we get higher in the system. If we expect the features, the morphologies, to be very large with respect to the sample space, we're going to have to pick an appropriately sized kernel to find those features in the system. Determining the kernel sizing is yet another hyperparameterization, right? The number of kernels and the shape of those kernels is something we can adjust. We're just going to go in and hit random numbers. We're going to start off with something and we're going to make adjustments to it. Yes?
So in this case, the image is basically black and white, but when you're dealing with like 3 colors, is that just 3 different inputs?
We decompose them into 3 coplanar individual color images, right? So you have an R, G, and a B. So the input becomes a tensor. So a color image will get input as multiple different, effectively grayscale versions of the color intensity in that spectra. So we'll talk about how we do color convolution as well. But we do that's a bigger portion of stuff like localization, where we do feature localization. But true, color images, right, do require an additional amount more. So that what's going to happen at that point in time? Every color is going to get its own filter activation. That doesn't necessarily mean that every color gets its own filters. No, but it can happen. There is a possibility that certain features in certain color spaces might be unique to that color space. But ultimately, we usually end up pooling them together by the end, right? So we sort of start that off running in parallel, right, as a chunk where we're convolving through the space as an area, right, moving through it as pulling the whole chunk out at a time, almost like that 3D combat style, right? And then when we do the pooling operations, we'll do spatial pooling for a while, and then by the time we get to the end of the space, once we've extracted the features of interest, we can then combine those pools together when we vectorize. So we'll end up with an image that's a vector, where you'll have the R, the G, and the B make up the vector components of it. And then all of those color images get what happens to that vector in the end. All those weights feed in to the final output spacing. So it's going to be taking a consideration for the features occurring and their co-occurrences as it results across the different colors within the image space. Okay. All right, I'm going to show you guys one other thing here. I didn't record this either, so that's intentional because I want people to wonder why there's no recording, right?
That will be funny.
Yeah. So we
Speaking
brought
of
a snake, right? Speaking of snakes.
Yeah, I was about to say speaking of
Yeah.
snakes.
So we want to do image classification, and we want to image classify apparently things people are scared of. I don't know why. It's a spider, a snake, and a dog and a cat,
Wait,
right?
why a dog and a cat though?
I don't know. A dog and a cat. Some people are scared of dogs and cats. Yeah.
Yeah, there are
Notice some of the things that are happening here. Let's look at the first operation. I colorize the standard backdrop of a vectorized version of the image, okay? This is the color activations for the likelihood of the regions within the spatial that correlate to it. This is one of those that probably is going to look a heck of a lot better on a monitor, right? Some of them, at least this portion of it looks a lot better on the monitor. I can go over here and I go, that's not the same picture. All right, so I can zoom in a little bit on it and we can see some stuff about it a little bit. Okay, that actually went the opposite direction. I have no idea what's happening. Why did it make it smaller? Okay.
It's too grainy. But
Yeah, it is a little too grainy, right?
yeah.
Why is it grainy though? Probably because it's gone through a lot of downscaling processes in order to get the output. But you can actually kind of still see the same, like part maybe along here. See the process along the edge of the screen? Okay? This is a standard backdrop methodology. Using what's called image saliency operations, we can see a higher resolution activation function. Saliency attempts to try to determine, based upon the visual space of the input, right, what the, reset this. Okay, there we go. It gets smaller again past 150, it's super weird. Saliency attempts to say which segments of the image are most likely correlated with the capacity for it to be classifiable. Here's an interesting note for you, just to think about this. Think about images of a beach. How much of that image, let's say you got 1,000 images of a beach. How much really different would those images be? Sky and clouds would make up like 65, 70% of those images, right? And the ocean, another 25% of it. Only a tiny amount at the bottom, sand, and a tiny amount of little palm trees at the top, right? The little palm tree segments in the center. The rest of the images are basically identical, right? So what separates your vacation photos from someone else? Saliency, right? What's important to you? So the importance is the determinacy. It's the ability to tell apart one set of information from the next. So the saliency says these are the regions of the image that I think are going to be most useful for classifiability of the output. Guided backprop starts to utilize information relative to visual clustering, visual spatial clustering, to make some determinations about the value of information within the visual space given the correlations of known visual tagging, right? Say this is the structure of the visual data that actually has the highest frequency components, right? So we have a high frequency transition, that'd be something like an edge is a high frequency component. So if I decompose this system, I note that the ground that the snake is on behind it has really pretty regular pattern, but the snake itself seems to be a divergence from that. So I can pick out and I can say, hey, the items that seem to be transitional between relatively smooth block operations can be used to guide the backprop operation to update the weights for these systems. We notice the little spider legs over here tend to be picked up a little bit because they're nice sharp edges. They have nice frequency offsets. Saliency with the guided backprop effectively is the map by which this process is guided, right? We use the saliency operation to tell it where to look for that output, right? Or I guess you'd say the opposite way around. We use the map, or we generate the map out from where the system has been trained to look. Okay? These are tools, once again, visualizations built for what? Humans. Computers don't need these, they don't care. They don't need to reconstruct the visual information in two-dimensional space. Why? Because they don't need to think about it in that way. Their precept says it's already encoded neurally within our space. I get it as a representation. Similarly to the way your brain does not store representations of visual information that you take in as whole 2D framed pictures, right? It shares it as a set of weighted connections based upon the higher level representations. If I was to link back this snake or this dog and this cat or this spider back to the concept of snake, dog, spider, I don't need to totally understand everything that makes that individual dog, snake, spider unique. I just need to understand that it is base spider and it has these unique characteristics, right? Base spider that is also yellow and has crazy creepy legs, right? That's the reason why I'm looking at it and saying I couldn't necessarily close your eyes right now and try to imagine the spider that I showed you up above. You're not going to have exactly the same one because you can only see a small amount of these salient representations of them. You can even look up there and try to imagine the rest of the spider based upon the saliency image. What do you notice? Your brain inpaints the rest of the spider. It's fitting it onto what it knows based upon that spatial representation. So as much as this seems obtuse, as much as this seems really odd and weird from the way in which we would go about it, the difference is that we actually can't look into our own brains and see how we process this information. Once it gets past sort of the visual, spatial characteristics that we are used to, all the rest of how it's passed off to the structures that recognize, correlate it, and store it are completely opaque to us, right? There's no correlation that we can apply in our head where we can turn inside and see how it works. We just have to try to process the information and see if it lines up with what we're expecting. We see some other saliency maps and weighted graded propagation, heat activation operations. Heat operations also utilize heat scale mapping in which the likelihood of there being value within the space is recognized as higher heat for the visual feature space. What do we notice here about the dog's face? Dog's face contains a lot of high density information, right? A lot of high density frequency. If I was to effectively pop this as a mask over the top of that image, I'd end up with just basically a fixed look at the dog's face. It's a type of segmentation in its own sense, right? I've now told you that the item that I thought was most significant out of that visual image space were the items and elements that are present in this area. Why do I do that? Because when I'm looking at the total number of activations for all of the kernels or all the weight activations in the system that are contributing most toward the classification of this particular image, I say they're all coming from here, right? I can track everything back to this one cluster of information, okay? Pretty much everything else there becomes what? Pretty standard. Everything else around it is something that maybe not necessarily as easy to determine as a animal or dog, whatever else might be the case, okay? We can look at a lot of different ways in which we go through guided segmentation process. Layer-wise relevancy is also an extraction process by kernel methodology, all right? And this one's kind of easy to see. It almost looks like kind of like a blotch style painting, right? Or maybe like an outline painting structure that you might even see a human attempt to replicate in terms of the ability to represent a visual image space with line drawings, right? That's what often happens whenever we extract and then recombine kernel activations, because you end up with things that end up stylized or posterized in this respect, where high intensity transitions will come out to look like this for our human mind, saying, hey, these are the regions, this is the segment of the image that has the highest structural density relative to information, all right? So this is an information density approximation. If we use different methodologies for hypergradient hierarchical visualization, this is VGG 16, all right? We talked about VGG. Remember that stacked layer-wise convolutional neural net, okay? This shows activations for class map activations, right? This says these are the regions within the system, and this heat map is inverted, all right? I don't know why this particular one is inverted. Maybe it's more visualizable. But the heat map shows here that the snake portion, which has effectively been outlined by the activation map, does what? It tells us which of the pixels, or what of the area of the visual space that the class is activating based on. This is interesting because this is part of how we backpropagate to that image localization space, right? How we get from these pixels correlate to this object. If we place a bounding box around this, which we'll look at next time, continue looking at this construct, but if we place a bounding box around this, we can say, hey, this is the region of the image that's the snake. We can also do what? Just multiply the activation kernel by the original image, and we can see which pixels, right, were actually being utilized for part of that segmentation process, okay? We notice here, by the time we get into the deeper layers, what happens? This makes plenty of sense to us. This makes almost no sense to us because it's become so muddied out,
Yeah.
right? So part of this is because there's a rescaling process that's taking place here. It's a lot of downscaling and operational pooling. Here's the other thing. There's a trick involved in this. What do you think the components of layer 30 of this system look like? How many times have they been convolved and then pooled and downsampled? Lots.
Lots.
Right?
Quite a
So
bit.
what am I doing now? I'm reprojecting that pooled and downsampled spatial representation back up onto the original image. The reason why this doesn't look like it matches perfectly with the original space is because it doesn't. It doesn't even map back to the same space, because the max pooling operation has dropped out some of the spatial characteristics, such that this mapped operation does not actually work perfectly to this original image, because it's been rescaled and had elements dropped out of it at every single one of those intersection layers for like basically every 2 pools. So even though this kind of relates or tries to map back what we saw as being highly relevant or highly salient in the original space, even the spatial correlations here do not necessarily track to the pixels of the original space, because what happens? Some of them have gotten shifted over, shifted around as they've been repooled and had kernels operating on them again. So keep in mind that even though this is useful as a descriptor at a level of trying to understand what's going on under the hood of this system, probably something like layer 15 or 20 of most networks, our ability to track back a good spatial understanding to the original image space is probably going to start to fall apart pretty hard, right? We're going to have to start thinking of it as a higher level system of recomposition and information reduction, compression, and retrieval, all right? I want to show you something down toward the bottom of this. There is a set of different conv layers and how the conv layers look for each of the activations in the system. These are actually the pre-trained feature kernels in color space for VGG. VGG learned these as features.
Is this for those specific images, or?
That's VGG, that's the network. No, those are the actual feature maps.
Okay.
Right? We've taken the kernel and we've sort of looked at those feature map operations. These are the kind of textures or texture information that the model is looking for at that relevant layer. Okay. I want to show you guys this one because I think this one's interesting. We were looking at it right beforehand. You guys have seen a lot of generative images. You remember back in the day when the generative images had some weird characteristics in them?
Yeah.
Look here.
Ugh, what the heck? Oh god.
What are those? Those are the kernels being activated to try to recompose the input image from the original input. That is how the system is convolving across the surface. Look like impressionist painting? Yeah, it does.
It does.
It's an interesting concept, but this is still actually just the network responding to the components of that original image space in that higher dimensionality space, red, green, and blue, right? And the filter activations on those components of the image. There are technically frequency components in here. Look, we have the same sort of spiral pattern, and what's happening to it? It's being repeated in different ways across the surface here. What is that an indication of? There are certain structures that have those kind of repetitions that are being found by the network as they're effectively being detected, right? There's your activations as it's spanning across the surface. Frequency, right, and the notion of there being changes in values and a certain pattern of operation, as well as changes in patterns of edges, are the methods by which we utilize extracting information from the system, right? The high-level approximations are just going to take this and continue to reduce it down, reduce it down, reduce it down, based on the kernel activation.
Is this related to what you were saying last week about shape theory and a lot of the...
Yeah, I said there's theories behind it. People have looked at things like utilizing Gabor filters, right? The interesting part is many of the networks that have utilized just a strict Gabor filter mindset. They don't perform as well as networks that are allowed to discover their own weighted kernel feature operations. It's an interesting relationship because we think that we're describing, right, the universe. We're describing every possible permutation of the system to the computer, right? But in reality, it says maybe there are actually some things underneath of this system that we don't even notice, right? Maybe it's able to see some insights that we could not have pointed out to it initially. The book's still open on it, okay? And every single network has its own set of these activation kernels, right? The ones I was showing you beforehand. These kernels and how they operate and what they pick up at each of the levels of the operation, right? These specific filters are optimized towards fine complexity of finding feature elements like the ones shown here. What do those image elements start to look like on this side? I find very interesting because it starts to look like the mosaic pattern that matches the sensor structure for a CMOS camera, right? The Bayer filter. Sometimes certain kernel activations will actually find that Bayer filter inside the image if it's a high enough resolution. And they will get rid of it by max pooling operations, right? Because as you drop out the feature localized spatial representations of them, the RG and B are already localized in that way on the Bayer filters, like this. Can work back to where the actual filtering process took place. It's fascinating. All right, guys, well, I'll talk to you on Thursday. Keep up the good work on your homeworks. Holler at us if you need some help with your backdrop, all right? Do that as robust as you can, but then focus on giving me some good quality outputs for your training networks, okay? Thank you.
The thing that immediately came to mind was seeing these texture patterns.
It is interesting because
Some of these, like,
there's something that's called filter processes in images that create resonance. Resonance have certain structured elements.
Email the TA.
All the image representations are in fact.
Excuse me.
I actually so you notice in certain resolutions
I realized that this entire time, even when I was like code and stuff, I had the long derivative of that.
And it actually doesn't mess with the output because I was hinging it some other way. I figured out why my equation was slightly different. Yeah, because he pointed it out.
You are talking to me. No, you were telling something. So, did you finish the whole back propagation part? And then doing the logic stuff, I had to do
Maybe we can see so I did like.
I have shift till 5, but I can figure out what it is sometime tomorrow. Till when will be free?
I will be, I can be at any time after 11 hours. I will be free, I think. I will be now. I've been working on that project and also doing other assignments.
Okay, so I can manage like an hour in between my shifts. So.
Okay, you let me know.
Okay.
So you're doing it here?
Probably, yeah. Oh, the chef part? Yeah, I work at ISL.
Oh. I never saw you.
I work inside, not in front of the
Okay, I applied for ISL. And is it a position? Did you also see but like, any other jobs?
No, it's the other job. So basically it's like, so when